Hey everyone, welcome back to CyberNetters. I'm Andrew Yick, and today we're talking about DHCP, which is the service that automatically hands out IP addresses so that your devices can hop on the network without manual configuration. We will cover in this video how DHCP works, the four-step process of assigning addresses, and how leases renew, and some security considerations. Let's dive right in. So let's start with the basics. A host needs two key addresses to function on a network. It's layer 2 address, which is the MAC address, and it's layer 3 address, which is the IP address. The MAC is burned onto the network interface card, or the NIC, so it is unique to your hardware and it doesn't say anything about how your network is organized. Meanwhile, the IP address can change over time or when you move networks. And DHCP helps automate assigning that IP address so that you don't need to have to set it up manually every single time because that would be a pain to do. Let's talk about allocating IP addresses for your devices. Sure, you could set an IP manually, but that's not always practical. IPs can change if you move networks or if the network layout changes, and some devices aren't always online. You might think about using a default address, but is that really a good idea? It could lead to conflicts if multiple devices pick the same default. Instead, we can dynamically assign addresses based on availability and network requirements, which is where DHCP comes in. It handles the hassle of handling out IPs, so you don't have to reconfigure devices every time something changes. Now let's talk about RARP, or reverse ARP. So this was an older protocol, RFC 903 by the way, that let a device broadcast a request saying, "Here's my MAC address. What's my IP?" The RARP server would then respond with the IP address that matches the MAC. However, RARP only hands out the IP address, but it doesn't provide other critical information like the default router or the subnet mask. So, while the RARP was a step towards dynamic addressing, it was pretty limited by today's standard. So that's why protocols like BOOTP and DHCP eventually took over because they can supply all the network settings a device needs, not just the IP. Alright, so let's talk about BOOTP, which is the Bootstrap protocol defined in RFC 951. It was a big step up from RARP because it not only gives an IP address, but it also points to the device to a boot file from an TFTP server, and it configures basic settings like the default router and the subnet mask. So how it works is basically in two phases, I should say. So the first step is when the device gets an IP and locates the server, and then it finds the boot file via TFTP. BootTP also uses UDP ports 67 and 68 and it broadcasts with 255, 255, 255, 255, which doesn't go beyond the local network. But there's also a catch. It only works at boot time and it doesn't support reassigning or renewing addresses without a reboot. That's why DHCP eventually replaced it. DHCP can handle address changes on the fly without rebooting the device. Now let's take a look at DHCP, or Dynamic Host Configuration Protocol, which basically takes BootTP's concept to the next level. Which is introduced in the early 90s, DHCP automatically sends network settings to devices on a TCP/IP network, which uses the same ports as BootP. UDP 67 for the server and UDP 68 for the client. So, important. DHCP works in a client-server model. So the server has a pool of IP addresses and network settings like DNS servers, gateway, etc. And the client just say, "Hey, I need an IP." DHCP also supports extra options beyond just the IP address, which is like specifying time servers, domain names, and more, which makes it like a one-stop shop for all your device's network's needs. Here's a quick look at the DHCP message format. It starts off with the OP code. One means a request from the client and two means a reply from the server. Then we have H-type, usually one for Ethernet and then H-line, 6 for the Ethernet's 6-byte MAC. Hops is incremented by relay agents if the request is forwarded across networks. We also have fields for the client's IP address, the server's IP, and the client's hardware MAC address. Now, let's talk about the DHCP message type, which each corresponds to a specific part of the conversation between the client and the server. They're actually sent in the options field of the DHCP message. So we have the 8 types, which is DHCP discover, DHCP offer, DHCP request, DHCP decline, DHCP pack, DHCP NAC, DHCP release, and DHCP inform, which these message types orchestrate the entire discovery, offer, request, and acknowledgement dance that makes DHCP so seamless for network devices. DHCP has flexible options field that can carry a bunch of extra settings. Beyond just IP addresses, it can provide things like the subnet mask, time server, DNS server, print server, or even a boot file name for network booting. This lets admins hand out everything a client might need to function on the network all in one go. So let's break down the four-step DHCP process. So you have the DHCP discover, which the client, which has no IP address yet, sends out a broadcast. Hey, can any DHCP server gives me an IP? And then this next step was the DHCP offer, which one or more of the DHCP servers respond with an offer, basically saying, here's an IP and some network settings you can use. And then the DHCP request, which the client picks one of those offers and then broadcasts a request. I'd like the IP you offered, please. And then you have the DHCP ACK, which the chosen server sends an acknowledgement, finalizing the lease. The client now has a valid IP address and other settings to use on the networks. This handshake happens very quickly, and this is what allows most devices to just plug into a network and get an IP automatically. So once the client gets a DHCP ACK from the server, the lease officially starts. The client also receives two timers, which is T1 and T2. T1 is half of the lease time. When it hits that mark, the client tries to renew by sending a DHCP request directly to the server. If that works and the server sends a DHCP ACK, the lease is renewed, and the T1 T2 get reset. But if that renewal fails by T2, which is at 87.5% of the lease time, the client broadcasts a DHCP request to any server it can find. If no server responds by the time the lease expires, the client must stop using that IP to go back to the full DHCP discover process. Essentially, T1 is your first shot at renewal, and T2 is the backup if T1 attempts fail. So continuing the lease process, if T2 passes without a DHCP ACK, the client broadcasts a DHCP request to all DHCP servers, hoping one can renew its lease. If none respond before the lease expires, the client loses its current IP and has to start fresh with the DHCP discover again. Essentially, T2 is your last chance to renew before the IP is given up and the client re-enters the full discovery cycle. APIPA, or automatic private IP addressing, is a fallback mechanism used when a host can't reach a DHCP server. The system randomly picks an address in the 169.254.0.0 range with a subnet mask of 255.255.0.0. It then broadcasts an ARP to check if anyone else is using that address. If it is taken, the computer tries another address up to 10 times until it finds a free one. This makes sure that the host at least has some IP, even if it's isolated from a proper DHCP server. A DHCP scope is basically the range of IP addresses and network configuration details that a DHCP server can hand out to clients. These addresses need to form one continuous block and share a subnet mask. If you need addresses that aren't contiguous, you can create one big scope and exclude the addresses you don't want to use. Also, note that one DHCP server can typically handle one scope per subnet, which keeps things organized. Scopes define what IPs are available and how the server will assign them, so they're a very important part of DHCP management. So, once you have defined your DHCP scope and excluded any addresses you don't want to hand out, what's left becomes the available address pools. These are your IPs your DHCP server can dynamically assign to devices on the network. Essentially, the scope says here's the full range, and exclusion says but don't use these. Whatever remains is fair game for clients requesting IP addresses. So now onto DHCP reservations, which this is where you tell the DHCP server, whenever you see this particular MAC address, always give it the same IP. It's handy for devices like printers, servers, or anything that needs a fixed address but you still want to manage it via DHCP. Essentially, it's a small carve-out in your DHCP pool that is dedicated to one device, ensuring that it always gets the same IP without having to manually configure static settings on the client side. DHCP by default doesn't have a built-in authentication mechanism, which raises questions like, how do we know this request is legit? And how do we ensure that this server is actually trustworthy? And without safeguards, attackers can pose as a DHCP server or client to perform man-in-the-middle or replay attacks. So to mitigate these risks, many networks implement DHCP snooping on switches, which tracks which ports can send or receive DHCP traffic, which blocks rogue servers. Some environments also use 802.1x for port-based authentication to ensure that only trusted devices connect in the first place. Most importantly, you want to validate both the client and server before handing out IP addresses or accepting them, or else you could risk someone injecting fake IP settings and hijacking your network traffic. And that wraps up our look at DHCP. We covered everything from RARP and BOOTP to dynamic IP assignments and lease renewals. Understanding DHCP is very important for any modern network environment. If you want to test your knowledge, head over to cybernetters.net. We've got quizzes on each topic to help reinforce what you've learned today. Thanks for watching, and as always, stay secure and keep learning with CyberNetters. See you in the next one.